Okay, let's jump right into this explainer and unpack the ultimate shortcut every planning engineer uses to bypass the staggering complexity of three-phase circuits. Last time, we figured out why the power grid actually runs on three-phase in the first place. But there's a huge catch, right? Solving a full three-phase circuit by hand, it looks like literal triple the work. Well, today, we're going to learn how to completely bypass all that heavy lifting.
So you're probably wondering, how exactly do you solve a three-phase grid without doing triple the work? I mean, trying to solve three interconnected phases all at the exact same time seems completely overwhelming. But there is this incredibly elegant mathematical key that just unlocks the whole system. And the big secret? You almost never actually solve all three phases at once.
And that mathematical key is converting a balanced delta-connected load into an equivalent Y-connected load. Now, why do we even bother doing this? Because a Y connection gives us something a delta doesn't: access to a shared neutral point right in the center. It's like finding the anchor for the whole circuit.
So here is the crucial point. You can collapse that complex delta network into a Y simply by dividing the delta impedance by 3. It's a beautifully simple formula. As long as your system is balanced, meaning the load impedances in all three phases are exactly identical, this direct mathematical conversion works perfectly every single time.
Now here's where it gets really interesting. Once every element in your network shares that central neutral point, the three phases become electrically identical, except for their 120-degree phase shift. And because a balanced neutral carries absolutely zero current, we can literally throw away 2/3 of the circuit and just model phase A against the neutral. This builds into what is honestly the single biggest simplification in power systems engineering: per-phase analysis. It's just 3 easy steps. First, you model phase A against the neutral. Second, you solve that one simple circuit using standard Ohm's law. And third, you take your answers and just shift them by 120 degrees and then 240 degrees to get phases B and C entirely for free. This is exactly why every textbook and every load flow program out there works in per-phase terms instead of clunky full three-phase quantities.
Section: Neutral Grounding and Protection, moving from math to the real world.
But, per-phase analysis alone won't show you everything. It assumes a perfectly balanced system. When a system develops a fault to ground, physical realities take over. Grounding the neutral point isn't just a basic connection choice. It is an absolutely critical protection decision to manage fault currents. In a grounded neutral system, you're providing a safe, controlled path for fault currents to return to Earth, which lets ground fault relays easily detect problems. In an ungrounded system, though, faults are way harder to detect because that return path is blocked. This is exactly why the grounding method is one of the very first things senior engineers check when they look at a new single-line diagram.
Section: The Sequence Networks, Solving Unbalanced Systems.
Okay, let's dive into what happens when a fault is unbalanced. Think of a single power line touching the ground, which, by the way, represents over 70% of real-world grid faults. When that happens, our neat per-phase trick doesn't work anymore. The solution? Symmetrical components. Originally developed by C.L. Fortescue, this brilliant method takes an impossibly complex, unbalanced three-phase problem and breaks it apart into 3 decoupled, super simple single-phase networks: the positive, the negative, and the zero-sequence networks. You solve each one independently using the exact tools we just learned and then combine them based on the specific type of fault.
Now, zero-sequence networks need some special attention. Unlike the positive and negative sequences, all 3 zero-sequence phasors are completely in phase with one another. Because of this, zero-sequence current absolutely requires a physical return path to ground or a neutral to flow. It'll flow easily through grounded transformer windings, but, and this is key, it is completely blocked by ungrounded delta windings.
All right, time for a quick check to see how these concepts actually tie together in your single-line diagram. Based on everything we've looked at so far, why do you think power engineers convert delta loads to Y before solving a circuit instead of going the other way around?
The answer is pretty simple. Y's neutral is the shortcut. You see, a delta connection has no neutral point to reference, which means you'd be stuck trying to solve incredibly complex loop equations across all 3 phases at once. The Y connection unlocks that neutral point, which is the exact mathematical anchor you need to isolate one phase independently.
Let's try one more quick check based on the sequence network rules we literally just covered. Imagine a zero-sequence current is traveling through the system and it suddenly hits an ungrounded delta transformer winding. What do you think happens to that current?
It is entirely blocked.
Because there's no physical path to ground, zero-sequence current simply cannot flow. And this isn't just some weird math quirk either. That ungrounded delta acts as an open circuit for zero-sequence current. Protection engineers rely heavily on this exact property when they're figuring out where they need to place their ground fault relays.
So, let's quickly review the major takeaways from this explainer. You now understand how the delta to Y conversion unlocks that all-important neutral point. You know that per-phase analysis lets you solve just one phase and get the other two for free. You can see why real-world physical neutral grounding dictates how we manage system protection. And you know that when unbalanced faults inevitably happen, we can model them using 3 decoupled symmetrical component sequence networks.
This per-phase mindset is the exact tool we're going to need for our next step, modeling massive grids. Real grids span dozens of different voltage levels separated by countless transformers. So how exactly do we wipe away all those different voltages to see the raw flow of power on one clean unitless scale? Well, we'll dive into the per-unit system in our next explainer. Until then, ask yourself, if we can simplify a massive 3-phase grid into a single line, what other impossible engineering problems are just waiting for the right mathematical shortcut?